All right, let's dive into a story that basically flips a 200-year-old mathematical rule on its head. We're talking about a problem that was considered completely unsolvable. Well, until maybe it wasn't.
So just think about this for a second. What if something that we've all accepted as a hard limit, a fundamental wall in our understanding of numbers, was actually just a giant misconception?
For literally 2 centuries, the brightest minds in math all agreed on one thing. A certain type of problem just had no perfect answer. Sure, you could get really close with approximations, but a pure, exact solution? Nope, impossible. So what are these problems? We're talking about polynomial equations. Yeah, I know, you probably remember quadratic equations from high school. Well, solving those is old news. Mathematicians cracked those, and even cubic and quartic equations centuries ago. But anything of degree 5 or higher, equations with x to the 5th power or more, that was a totally different story. That was considered a dead end.
And look, this wasn't just some gut feeling they had. No, this was a hard and fast rule in the world of mathematics, a wall built on the foundation of a very famous theorem.
And here it is, the big one, the Abel-Ruffini theorem from way back in 1824. It basically states there's no single formula to solve these higher degree equations if you're only allowed to use the standard stuff, adding, subtracting, multiplying, dividing, and taking roots. For 200 years, that was the final word. End of story.
And this quote right here, it just shows you how huge this idea was. It wasn't just some obscure theorem, it was seen as the literal boundary of what was even possible in algebra. Okay, so you've got this unbreakable wall. But what happens when someone just walks up and decides to challenge it? Well, this is where our story takes a seriously revolutionary turn. And that's where Professor Mourad Sultan Ezouidi comes in. This one statement says it all. He's basically standing up to 2 entire centuries of mathematical consensus because he just refused to accept the word impossible. Now, this isn't just some random guy with a wild idea. Professor Ezouidi is a serious, internationally recognized mathematician. He actually developed a whole new method called Ezouidi's theorem that he claims does the very thing the Abel-Ruffini theorem said couldn't be done: find exact, perfect solutions for these super complex equations.
So the big question is, how? How did he possibly pull this off? Well, it all comes down to a completely new way of looking at the problem. Let's compare the old school approach with his revolutionary new method.
So think of it this way. The classical mathematicians, like Abel and Galois, were working with a specific set of tools based on things like field theory. And with those tools, they were absolutely right. You couldn't build a solution. But Ezouidi, he basically went and invented a whole new toolbox, using these incredible ideas like recursive structures, kind of like mathematical Russian nesting dolls, to attack the problem from a totally new direction.
And when you lay it all out like this, the difference is just, wow, it's night and day. The old methods hit a wall and had to rely on good enough approximations. Ezouidi's theorem claims to deliver exact 100% verifiable solutions. But you know what's really profound? It's the philosophy. One side accepted limits. The other rejects what it calls mathematical fatalism. I love that phrase.
So let's try to picture how this works without getting lost in the weeds of the math. Imagine the equation is this giant, messy, tangled-up knot. Ezouidi's method first sort of reorganizes that knot into a neat series of smaller, nested loops. Then, it uses these special transformations to loosen each loop one by one. And finally, it uses this brand new process to just gently pull out the exact solution until the entire knot is undone.
All right, so talk is cheap, right? Especially in mathematics. You need proof. You need to see it in action. So now, let's look at the ultimate test, taking on a 20th degree polynomial, something way beyond that classical limit.
Just look at this thing. This is the monster, a 20th degree polynomial. You can totally see why everyone for 200 years just threw their hands up and said, nope, can't be done. It just looks impossibly complicated. And yet, here is the solution presented in the source material. Now, the full roots are incredibly long and complex, but they are all built from these perfect, exact symbolic components. Look at that. There are no decimals, no rounding, no close enough. These are presented as the pure 100% correct building blocks. The contrast between that chaotic problem and the elegance of these components is just stunning. It's an incredible demonstration of the theorem's claim.
Okay, so this is huge. But what does it all really mean? What's the bigger picture here for the future of mathematics?
And this is probably the most important thing to get. This isn't about saying Abel and those other brilliant mathematicians were wrong. Not at all. They were completely right, given the tools they had. This breakthrough just suggests that their toolbox wasn't complete. Someone just came along and added a whole new set of game-changing tools. And the source material really puts a fine point on it, calling this the start of a whole new era. An era where that old line between solvable and unsolvable polynomials might just get erased completely. Just think of what that could mean for fields like physics or cryptography that depend on this kind of math.
Which leaves us with this one last thought, and it's a big one. This whole story, it's not really just about math, is it? It's about how we define impossible. If a wall that stood firm for 2 centuries can just disappear, what other things that we think are impossible today are just problems waiting for someone to invent a new toolbox?